Okay, so for this video, we're going to revisit diodes and maybe have a proper discussion about what they are and how to use them. So from the Intro to EE course, we know that diodes are semiconductor devices, but for the purpose of this course, we'll loosely define it as sometimes it conducts, sometimes it doesn't. It depends. Now, our common diode that we're going to refer to, here on the left we have our circuit representation of a diode, and you have an anode symbolized by the letter A and a cathode by the letter C. Now commonly when we talk about the voltage over the diode, we're going to be talking about the voltage from the anode to the cathode, sometimes represented by V capital D. Now if we look at what we primarily use this common diode for, well, it's going to be used to allow current to flow in one direction, and the direction that it flows is anode to cathode. So we could define some current that looks like this and call it ID. Now to define the current, we have to go into some of the semiconductor physics, but we're not going to do that in this course. In this course, we're simply going to say that the current can be found by the Shockley equation, which is given right here. So the current through the diode is equal to the saturation current, IS. That's going to be multiplied by an exponential. Inside that exponential, we have Q, which is the charge of the electron, V sub D, which is the diode voltage, or the voltage over the diode from anode to the cathode. We have N, which is the emission coefficient. Usually you'll see that as either 1 or 2. We have K, which is the Boltzmann constant. We have T, which is the temperature in Kelvin. And then we have this -1 term here. Now, typically we're going to see N equal to 1, and the saturation current is usually on the order of 10 to the -14 amps. So quite a small value. But we also can define KT divided by Q. That's going to be what we call our thermal voltage, and at room temperature, it's about 26 millivolts. Now, in a previous course, we defined something called the dynamic resistance, and we modeled it like this, and we did an approximation such that it was equal to this term here. Now, I'll link that video where we went through this in the description. And while you're in the description, might as well like the video, comment, subscribe, share, all that fun stuff as it helps the YouTube algorithm. But nevertheless, we can look at a circuit right here on the right. Very simple circuit, and we're just going to set up a KVL. Well, this led to the diode voltage being equal to this messy term here. Now for reasonable values of the voltage and the resistance in the circuit, we got that the diode voltage was approximately 0.6 to 0.7 volts, and that was going to be at room temperature. You could get that value to change pretty drastically if you messed around with the circuit in the right way, but then this approximation doesn't really hold, and you have to go back to the Shockley equation. Now, to get into that, there was a comment on that video, which is now over 2 years old, and the question was, why is the resistor needed for the derivation? Of course, a 0 ohm resistance would leave no current regulation, but how do you solve for this case? And if I'm understanding this question correctly, so we're going to say that in our previous circuit, R is equal to 0, so then the voltage over the diode is simply going to be our source voltage that we apply. And we should have some knowledge about what that voltage is. So from that, we can plug it into the Shockley equation right here. So assuming we would know all of these values, VD is going to equal our source voltage. So we can just make that substitution right here. And based off of what that voltage is, we should be able to find the current going through the diode. Now, if we don't know the voltage over the diode, but we know what the current going through is, well, we can just reverse this equation to find the voltage as NKT divided by Q, and then we have the natural log of our diode current plus the saturation current divided by the saturation current. Now, commonly in university, you'll see this kind of IV curve for the diode, and we talk about 3 regions of the diode. So the first region is going to be our forward bias, so that's going to be over here on the right. We know how that should work. Second region is the reverse bias, so that's going to be this regime here on the left. And ideally, we'd like to say that no current flows, but some current might, and it might be in the nanoamps, but it is some small amount. Maybe you can neglect it to 0. And then 3, we have this breakdown voltage, and that occurs right here. So that's pretty much when the diode fails. Now in the industry, where you might see a data sheet that looks like this, so notice now horizontally, we have the voltage, and vertically we have the current right here. So you don't really get the breakdown region And you may get some kind of reverse voltage, what that is, in one of these values. But again, similar to the op amp, there is a ton of stuff in this data sheet that we're not even going to consider for now. It'll be maybe in the advanced electronics course, but there's things like total capacitance, thermal resistance, and a lot of other things that are really important when you start to design critical things with electronics. But for basic circuit creation, someone just trying to learn, we can just pay attention to most of the stuff up here. Nevertheless, we can do something called a load line analysis for the diode to kind of more accurately predict the current. So we're going to have our basic circuit like this, and we're going to set up a KVL, so everything looks pretty familiar. Now, if we're able to curve fit and plot out the IV curve from the datasheet, what we can do is set up a few boundaries, and this will help us with our load line analysis. And we're going to do this for the voltage of the diode and then the current through the diode. Now, how we're going to do this is we're going to set up that the diode voltage is equal to 0 in this original equation up here. Now, if that's the case, then we simply set up that V equals ID times R. So we're just using this part of the equation right here. Or we can say that the current is equal to V divided by R. So in the vertical section of the graph, we would note down what that value is. And now we can do a similar thing, except say that the current through the diode is equal to 0. So now if we do this, we actually know that the voltage over the diode, which we can substitute this term right here as VD, that VD is going to be equal to the source voltage. So we denote that right here. Now, if we have both of these points in our IV curve plotted out, what we can do for each and individual circuit, ignore my very poorly drawn line, but where we would have an intersection right here, that's where we would pull the values for the voltage and the current in a more accurate representation, rather than just assuming a 0.6 or 0.7 volt drop. Now, we can use diodes to allow current to flow in one direction or block current from flowing backwards if needed. Usually we don't want to be in the reverse bias region near the breakdown voltage. I mean, if you're in the reverse bias region because you're trying to block current, that's okay, but if you're getting close to that breakdown voltage, probably try to stay away from there. But we have another type of diode that's actually okay with this, and that's going to be the Zener diode. Now, it's similar to the common diode that we have before. We have another IV curve, but if we look here at the breakdown voltage, it's actually designed such that if, let's say, we attemptively reverse bias this diode and push it and push it and push it in a familiar circuit that we had above, any amount of current that will flow through now, your Zener diode is going to clamp at that voltage and it's going to hold that voltage. Obviously, there's power considerations that you don't want to burn up your device, but realistically, these diodes are designed to kind of hold this voltage per se. Now you may ask, how do I know if I have a Zener diode versus this common diode? Well, with our common diode, we know that symbol look like this, where we had anode and cathode. There's Zener diode. We get some little squiggles off this vertical line. Again, we have an anode and a cathode. If I was going to denote this, I would denote this as D1 versus the Zener. I'd denote it with Z1. And we'll look at how to use both these diodes in the next few videos. Thank you for watching. We'll see you then.